Okay, sorry about that. Had a little bit of a technical issue, but I think we're back. If there was anybody who was on the YouTube stream and got bumped, I apologize. I was just having some technical issue, so I think I've got it taken care of. I think we're all working properly. Everything looks like it's set up. If there's any kind of issue, let me know in chat, and then I'll see what we can do about it, okay? All right. Welcome on in. We are still moving quickly towards the end of the semester. We need to, we don't have to rush, but we do really, need to pay attention. This was a 15-week course, so we lost 3 weeks of time to spend on stuff. We're going to move a little bit faster, which is still not crazy fast. I have a stats class that starts tomorrow, and they have, 5 weeks to finish the course? That's crazy fast. But just at least you're not in that situation. They're going to be doing like 2 to 3 chapters a week. Okay, so we are getting into probability. Most of your assignments for probability are due November 9th. And you see here I've got your statistical conclusions. Those are going to be due, okay? So here's the thing about those statistical conclusions. They're kind of a rough draft, right? Think of most of these as rough drafts, these group project pieces where you go in and you leave a post and you get points for that. Think of it as a rough draft. If you get full credit for it, it doesn't mean that your work is great. It means I see that you went in there and you tried to learn the tools that you need for this section and you tried to apply them to your data. That's good. But I don't expect you right when you learn this stuff to be really good at it. So here you want to start formalizing your conclusions, your ideas. Like what were you thinking? What are you trying to try together? Are you trying to tie together work hours and units taken as a student? Right? Then start trying to formalize those conclusions, trying to put them into the form of an idea that says, we think that the number of as the number of units taken by a student goes up, their work hours decreases or their work hour increases or whatever. And then try to give some evidence. Remember, what you're really doing here is think of it like a lawyer. You're trying to make a case. You have a narrative about a series of events and how they took place, and you are trying to use evidence to convince people that your narrative is the correct one, right? That's what you're doing here as statisticians. You're trying to say, we think that as people work more, they have less or as people take more units, they have less time for work, so they work fewer hours. Our data shows this, and here's how our data shows that, and then you can give some evidence. Okay, so don't, I don't expect the conclusions you write here on November 21st to be the same ones, word for word that you have written in your or that you give in your final project. They should be improved by then because you'll have more statistical tools. You'll have a better understanding of statistics. But right here, just go in there, try to come up with some conclusions that you think are realistic. Try to just use it as an exercise to put things together. It's an easy 10 points. This one's a little more challenging than the earlier discussions that you got points for, but it's not too bad, and you're going to have to do it anyway. So you might as well start that process now so that when you think about it again in 5 weeks, you're going to be better prepared for it, rather than if the first time you think about it is 5 weeks from now, you're still going to be kind of lost, okay? And then you've got some other stuff due not too soon after that. This is kind of a shorter chapter, but we need to get into that as well, so that you can go through and finish that. In fact, we kind of backing up against 3 chapters in a row. I'm gonna have to move this one to a little bit later to give you a little bit more time to work on that. So chapter 7 I'll probably have to give a few more days to work on, but chapters 5 and 6 you can see are coming up due pretty soon. So we're talking about probability. So we want to get into that kind of stuff. All right. So make sure you're working through these. So probability, right? A lot of people don't learn probability. I can tell you firsthand that most people that you run across have no concept of how probability works, which means they end up using it incorrectly a lot of times. Like you've heard me complain about people using statistics incorrectly. All you have to do for that is just listen to any politician talk for very long, and they'll probably say something which is statistically unsound, right? It's the same thing with probability, and probability falls into that area where people are like, why do I have to learn probability? Why do I need to know this? Well, partly you cannot understand statistics if you don't understand probability. It relies so heavily on probabilities that it's everything in statistics. If you take probability away, there is no statistics, okay, except for the very basics of like mean and median. Issues with my connection here. So if I froze there on screen, there's some kind of connection I'm having trouble with here on the with YouTube, but hopefully that was just a little blip. So what was I saying? People don't understand probability too well, right? And as a math professor, you hear this a lot where it's like, why do I have to learn this? Well, that's what I was saying. You need to learn it for statistics, but also probability is one of those things that you can use every single day in your life to help you make good decisions. You use that probability. And here's the thing that, like, a lot of times when people come to me and they ask me, why do I really need this? Well, it's like reading, right? If you couldn't read, would you die? Probably not. You probably could survive in the United States if you couldn't read. But would you miss out on a lot of opportunity? Would you probably make a lot of bad decisions because you didn't have all the information that you needed? Yes. Math, and specifically probability, is the same way, right? You can use probability every single day to make good decisions, good financial decisions, good decisions about your health, good decisions about, especially at the vaccines, social distancing, when should you go to the store, all that kind of stuff. All sorts of decisions you can make. Now, if you choose to ignore that, go ahead, but then you're putting yourself, you'll make decisions that are not fully informed. So probability is important not only for this class to understand anything past this point in the class, which is kind of the big statistical tools, but also you can use this in everyday life, because the reality is, the point of like corporations in this country is to make a lot of money, right? To make a lot of profit. They understand probability, and oftentimes, it's the same thing with the politicians speaking. They know how to trick people into thinking a thing, and they kind of use a roundabout way of explaining things to make you think a certain way, and you want to be able to sort of defend against that and say, actually, that doesn't work that way. All right, and probability is all like this. We'll see this when we talk about casinos. How do casinos trick your mind into thinking that you have some kind of an advantage, and they get you to put more money on the table, right? All these kinds of things. And where if you understand probability, you're not going to fall for that kind of stuff. So let's get into basic probability. We'll learn this for, part of a week, and then we'll go from there. So we need some definitions to start off. So we have an event. An event is a collection of results or outcomes of a procedure. So our procedure could be to flip a coin 100 times and record the results. So then an event would be one flip of the coin. Okay, I could roll a dice. One event would be one roll of the dice. Okay, or maybe we're playing craps. We roll 2 dice and we add them together. Rolling 2 dice and adding them together, that's one event, right? So it's like one procedure that you're keeping track of in the larger number of things. A simple event is an outcome or event that cannot be broken down further into simpler components. So flipping a coin, I flip a coin, it comes up heads or tails. I can't break that down any further than that, right? If you take away the flipping of the coin, then nothing happens. And if you take away the observation of it being heads or tails, then you don't have a record of what happened. So flipping the coin one time would be called a simple event. Now, this next one we're going to look at is one that I think a lot of times people are like, they find it confusing, and they're like, I'll just skip understanding that piece. You cannot do any probability unless you understand sample space and you understand how to count the size of the sample space. So for probability, sample space is way more important than people tend to think it is. So, you definitely want to, when you're working on this stuff, take a little bit of time to sit down and make sure you understand what the sample space is telling you or about the problem that you're working on, because without it, there's very, very few problems you're going to be able to get done in probability without understanding the sample space. And it's not actually that complicated. Once you get a little bit used to it, It's not as bad as some people kind of, it's one of those things that looks scary at first, but then when you get into it, not so bad. The sample space for a procedure consists of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. So, that's a good definition, but we can think of it even in simpler terms. The sample space is the set of possible outcomes. Okay, so if I flip a coin, what is my sample space? Well, I would probably write my sample space as the following. I didn't think I was going to use this page today, but now I see I am. So let me clean it up here a little bit. Okay, so here's our, so sample space for a coin toss. Okay, so for a coin toss, what are the possible outcomes if I flip a coin? Well, it can come up heads or it can come up tails. So this is the sample size. And a thing you're going to be doing soon, measuring the size of the sample space. How many things are in our sample space? 2. There's 2 possible outcomes. You can flip a coin and get heads, or you can flip a coin and get tails. 2 outcomes there. Okay, what if I wanted the sample space of a dice roll? Well, what are the possible outcomes if you roll a die? Well, you can get 1, 2, 3, 4, 5, 6. Right? That's my sample space. Oops, I didn't write space, but yeah, let's go ahead and write it in there. Sample space. So our sample space for a coin toss is heads or tails. Sample space for a dice roll, 1, 2, 3, 4, 5, 6. Now we get into problems that can be more complicated, but if you always just go back to these 2 examples, it should help you remember, okay, the sample space is just the list of possible outcomes. Okay. And then you can slowly start to work through the more complicated examples that we'll get through. Okay. So here they have an example of people trying to have children, and what are the possible outcomes of a boy-girl, right? So if you're having a single birth, there's 2 outcomes. You have a boy or you have a girl, right? Or 3 births, how many possible outcomes are there? Well, and when you're listing these, you want to do it in a systematic manner. You'll learn this when you're doing the homework, how to list things systematically. If you're just randomly trying to come up with all the probabilities, you're very likely going to miss one. Or if your list is long enough, sometimes you list the same one twice and don't realize it. So you want to be kind of careful. So your outcomes could be boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. So 8 outcomes. If you have 3 births, they're listing 8 outcomes possibly. This is sort of a oversimplified example, right? So remember, this may not fit the real world as far as children being born, but sort of think about the theoretical situation of boys and girls being born here, right? So how is that list systematic? Well, what you generally want to do is you start at one extreme, and it doesn't matter which one you do. Here they started with boy, boy, boy. If you wanted to start with girl, 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 it's perfectly fine, right? But then what you do is you come up with all the ways of changing the last situation. So see how the next one in this list of 3 became the boy, boy, girl? That one switched. Well, now that you have those 2, you've listed all possibilities of starting boy, boy. Then you move to the left. So now they change the one in the middle, and they go boy, girl, boy, boy, girl, girl. Now you have all possibilities where the middle situation, the middle position, is what I meant to say, is girl. Then you say, okay, now let's try all those situations the positions where it starts with girl. Girl, boy, boy, girl, boy, girl. See how they're moving? They start at the right, moving them when they can, and then they move to the left. And eventually you get to girl, girl, girl. Okay? So that's, here you have, for 1 child, your sample space has size 2. For 3 children, sample space has size 8. It's actually 2 to the third is why it's 8, 2 cubed. You'll learn some of this as we go. Okay, notations that you're going to need to learn, and these are standard even outside of statistics. This is the kind of notation that you see used in probabilities. So capital P denotes a probability. Guess what? We're also going to use lowercase p throughout the course, and guess what that stands for? That's also a probability, but it's generally for a specific case when you see lowercase p. But when we're talking about these statistics, capital P is the probability that we're talking about. A, B, and C are events. They denote events. So when you see it this way, this looks like our function notation, right? It is a function, right? It's the probability of event A occurring. Denotes the probability of that thing occurring. So you could put it, what you put inside, sometimes you write it out. So you could put like P of tails. If you know that you're doing on a problem that you flip a coin one time and see what you get, you could just write it in here, P of tails. What's the probability of getting tails on a coin flip? And then you'd get to 1/2, right? So that's just our notation that we're going to use. Okay, so let's actually get into what probability is and what probability is not. So this confuses people a little bit because there's actually multiple types of probabilities. So let's start with the classical approach. I always think classical approach should be first, and then we could talk about relative frequency approximation of probability, which is kind of a very fancy way of saying sort of applied probability. So the classical approach to probability, I'm looking at number 2 right now is what we're working on. Classical approach to probability requires equally likely outcomes. That is hugely important. That seems like a little detail. That's not a big deal. Whether you have equally likely outcomes or not totally determines which formula you're supposed to use. And I know even looking at these two formulas, you're like, I don't know, they kind of look the same. But the information that you're putting in these fractions comes from different places. So you have to ask yourself, do I have equally likely outcomes, right? Is this a coin flip where it's equally likely that I'm going to get heads versus tails when I flip a coin, right? Is this a dice roll where I'm assuming all this stuff is fair? Obviously, you can doctor up a coin a little bit. You can shave the corners on a dice a little bit. But we're assuming we're talking about a fair dice, fair coin. Those have equally likely outcomes. Not everything in life has equally likely outcomes, but a common mistake that people make is they go into a situation that does not have equally likely outcomes, and they still use this way of calculating it, and everything falls apart. I'll give you a sort of an extreme example in just a moment when we go up and talk about number 1 here. So if we know that we have equally likely outcomes, assume that a given procedure has n different simple events and that each of those simple events has an equal chance of occurring. So flipping a coin, rolling a dice, something like that. If event A can occur in S ways, in S of these n ways, then P of A is equal to the number of ways A occurs over the number of different simple events. So that seems confusing. It's actually much simpler than it seems. So for instance, let's go back to our example over here. I don't know why I didn't think I was going to use this. Now I'm using it all over the place. So let's do a dice roll. You have one die. I think die is the single of dice, right? But you've got a die. We're going to throw a dice, see what's on it. Actually, I meant to do the coin first. Let's do a coin flip first. Then we'll do the dice roll. So a coin flip, well, what's our denominator right here? The denominator says the number of different simple events. Does that sound familiar to anybody? The number of different simple events is the size of your sample space. It's just the number of different ways that everything can occur. So if you have, let's look at the probability of getting tails when I flip a single coin. Well, the denominator is the size of our sample space. It's the total number of ways that things can occur when I flip a coin. There's 2 outcomes when I flip a coin. It comes up heads or it comes up tails. So there are 2 outcomes from this. How many different ways can I flip a coin and have it come up tails? 1. That's that I flip the coin and it comes up tails. So there's one way out of the possible two. So that our probability is 1/2, right? 1/2, which makes sense. Yeah, when I flip a coin, my probability of getting tails is 1/2. The probability of heads is 1/2, right? So that makes sense. Let's see. Sorry, I was going to say something and then I forgot what I was going to say. Oh, keep in mind a probability when we're strictly speaking, when we're talking about probability from a mathematical standpoint, probabilities are a number between 0 and 1. They're not a percentage. They're not like odds, right? They're not any of that stuff. It's a number between 0 and 1. Now, sometimes we'll kind of loosely speaking talk about probabilities as percentages. I'm just realizing I didn't have any water yet. I'm going to have to go get some in a minute. So, you know, if you could be forgiven for talking about flipping a coin and saying the probability is 50%. Technically, that is incorrect, but there is a translation there which says the probability is 1/2, meaning half the times that I flip a coin, I expect to get tails. That translates to 50%. So your probabilities can be loosely converted to percents, but you have to realize that percent's going to vary. We're going to talk a lot about variation when we talk about these probabilities, right? So you just take the size of your sample space, you put that in the bottom. You take the size of the thing you're talking about, how many ways can that occur, and you put it in top. So let's get a little bit more complicated. Let's do a dice roll. So I'm rolling one dice. So what is the probability that I will roll a prime number? Let's see. So the probability of rolling a prime number Okay, so I always figure the denominator out first because it just makes more sense to me. What is the size of our sample space for a dice roll? How many possible outcomes are there when I roll a dice? Assuming we're talking about a normal 6-sided dice, right? We're not talking about like a Dungeons and Dragons dice or something like that. 6. There's 6 ways for that to occur, right? Okay. So our numerator is how many ways can the thing occur that we're looking for? Well, I'm asking about prime numbers. How many prime numbers are there between 1 and 6? So let's see. 1, no. 1 is defined to not be a prime. 2 is a prime number. 3 is a prime number. 4, no. 5 is a prime number. Is 6 a prime number? No. So let's see. Is that it? 2, 3, 5. That's all of them, right? So there's 3 out of 6 possible ways to get a prime number, which is something that probably most people didn't know or ever even think about before we started. But now we know, oh, the probability of rolling a prime on a dice is 1/2. And yes, of course, we simplify that fraction, right? Anytime a fraction comes up, somebody's going to ask me, should I simplify the fraction? And the answer is always yes, right? It's actually less work to simplify the fraction than to ask if you need to simplify the fraction. But the answer is yes, simplify that fraction. So 1/2. Oh, so the probability of me rolling an even when I roll a dice is equal to the probability of me rolling a prime. No, we didn't think about that before we did this, right? But they come out the same. Okay, so that's your basic for probability. Remember, that is only when every outcome is equally likely. So here's a way that people will misuse this. They'll come in and say, okay, well, let's just say you're watching the, playoff basketball, NBA playoffs, and Steph Curry's at the free throw line, and it's a really important shot. Him making this could mean the difference in the game. It's towards the end of the game, and you're thinking, what's the probability that he's going to make this shot? Right? And what I'm about to explain is the wrong way of thinking about it. Is you go, okay, let's see. Well, there's 2 possible outcomes. He's either going to make the shot or he's going to miss it, right? So my denominator should be 2. And how many ways are there for him to make the basket? 1, he makes the basket. So then doesn't that mean his probability of making the basket is 1/2? No, because we ignored this big bold parentheses right here. We use the formula that requires equally likely outcome. Steph Curry shooting free throws is not like someone rolling a dice. Okay, he has shot in his lifetime hundreds of thousands of free throws. He's gotten very, very good at it. It is not an equally likely outcome that he misses versus that he makes it. So that's an example of using the wrong formula at the wrong time. Or the, excuse me, you see what I'm saying? So in this case, we can't use this equally likely outcome that we just did for dice and coins. We have to turn our heads to something different. So think about the announcers during that basketball game. That, you know, these announcers need something to talk about. Otherwise, there's dead air and people get bored. What are they probably going to be talking about? The probability of him making it. How do they figure out the probability of him making it? Well, there's kind of a couple ways you could do this, depending on, you know, how much data you have and how much you want to talk about. But what you would do is you would go back and you could look at all the free throws that he's attempted. That would go in the denominator. And all the free throws that he's made, and you would put that in the numerator. So you could either do it, you know, they do this when they're talking about sports. You could either go back for the entire season and say, well, this season he's shot this many hundreds of free throws, and here's how many hundreds of free throws he's made. And that's oftentimes called experimental probability, although here they call it relative frequency approximation of probability. I think it just makes sense to call it experimental probability is what a lot of books call it, because you're doing it from experiment. Each time you watch Steph Curry shoot a free throw throughout the season, he's conducting an experiment, and they're keeping track of his free throws, right? The other thing they sometimes do in that situation I described was they talk about his playoff numbers, right? Because maybe his playoff numbers are a little different than his regular season numbers. Who knows? But what they, in that same case, they would say, well, during the playoffs, he shot this many free throws, and here's how many he made. So you put the number of times he made free throws in the numerator, the number of times he attempted them in the denominator. That fraction is the probability that you expect to see. And it approximates his true probability of making the free throw, right? So our formal definition for this, relative frequency approximation of probability: conduct or observe a procedure and count the number of times that event A actually occurs. Based on these actual events, P of A is approximated with the following. Now, the higher time, the more times that you make observations, the better your probability is going to get, right? We'll talk about this. It's called the law of large numbers. We'll talk about this soon. But you can understand it from thinking about the extremes, right? That would be like if I don't watch basketball very much and I show up and I see Steph Curry shoot one free throw and he makes it. And I go, okay, well, I watched him attempt one basket and he made that basket. So the probability is 1. Yep, the probability of Steph Curry making a basket is 1. We expect him to make 100% of the shots that he makes. What was my error there? Where was my bad statistics? It's because my sample size is 1. That's not very good, right? What if he missed that one shot that I saw him take? Then I would just assume that he makes 0% of his shots, that the probability of him making it is 0? No. With something like that, that's why it's helpful. Steph Curry shoots hundreds of free throws throughout the season. Then you start to get like a reasonable measurement, right? Once he's shot maybe 100 shots, you kind of start to believe, okay, well, he makes about, 90% of the time he's going to make a shot. So it makes sense that the more times you conduct this experiment, the better approximation you're going to get, okay? And the difference between the two is just, are they equally likely outcomes or are they not? Okay. Then we've got this subjective probabilities. P of A is the probability of event A is estimated by using knowledge of relevant circumstances. So that's just kind of a mixture sometimes of a little bit of both of these. Can be. Right. Okay. And here we go. Law of large numbers. I thought it was a few pages down, but it looks like we're here already. So this is what I was just alluding to. The law of large numbers says, as a procedure is repeated again and again, The relative frequency probability of an event tends to approach the actual probability. That means that if we watch Steph Curry for one game, the probability that we measure of him making a basket is probably not going to be very good, right? So, basketball players have off nights and they have nights where they're just they're hitting them all. That's how probability works. You get fluctuations and stuff, right? So what that means is, though, after an entire regular season, we look at his free throws, we have a much better understanding of his probability of making a free throw, right? So as the procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. Okay, now this gets confused with what people call the law of averages. And the law of averages, I'll even hear this. Sometimes you're listening to a podcast, even with like people that are well educated, they'll talk about the law of averages, and the law of averages is not a thing. It's actually wrong. It's incorrect. But it's what happens when people learn the law of large numbers, but they don't really understand it. In their brain, they form this thing called the law of averages. And the law of averages is, as I said, mathematically wrong, but our brains kind of snap into that sometimes. There's a number of different things in probability where our brain really wants to think a certain way, and we have to force it and learn not to think that way because it is incorrect thinking. So the law of large numbers just says as you do lots of trials, your probability is going to more likely approach the actual number. Think of it this way. If I gave everyone a coin, say we take a fair coin, or you pick your own coin so we think it's a fair coin, and I tell everyone to flip a coin 5 times. Well, most people are going to get, 2 tails or 3 tails. That's where we're going to see most people fall. Some people are going to get 4 tails and 1 heads. Some people are going to get 1 heads and 4 tails. There'll be some people on the extremes. We might get one person in the class, maybe a couple, that get 5 tails and no heads, and then they'll flip. But it's like no one's going to freak out, right? If we all flip a coin 5 times and it comes up tails 5 times, we're not going to like call the newspaper and be like, you got to come down and report on what we just saw. This person flipped a coin and this coin comes up tails 100% of the time. Right? That would be ridiculous. But what if we had a coin and you flipped it 10,000 times and it came up tails every single time? Now we're going to start getting a little weirded out and think that something very strange is going on. Because the law of large numbers says if you keep conducting this event, it should start to approach the actual probability, which should be 1/2. So if we flip a coin 10,000 times, you're not going to see 80% of the time it came up tails. That's just not going to happen, right? The probability of that happening is so extremely low that it would be absurd, right? We could have every human being doing this round the clock for thousands of years, and you're not going to have someone who flipped it 10,000 times, and get all tails. It's not going to happen. So we sort of intrinsically understand, oh, yeah, that makes sense. The more times I conduct the trial, the better my numbers are going to get. Because if you just think about the extremely low numbers, you can see really weird behavior. But if you conduct that experiment 1,000 times, you don't expect to see that kind of weird behavior anymore. Here's where people go sideways, and here's how this tool is actually used against you. We'll talk about an example where it's used against you in the casino. So I remember when they started doing this kind of in the 90s. If you're walking through a casino and you go by the roulette table, okay, it used to just be there was a roulette table. And if you weren't paying attention, you could walk right by it. It just looks like a bunch of people sitting at a table, right? Now what they have at these roulette tables is there's a big sign above them. And what it does is it shows you the past like 20 outcomes, maybe 10 outcomes, but usually it's like 20 to 15 outcomes. And they show you with the color. So on a roulette table, you have a bunch of numbers. Almost half of them are black, almost half of them are red, and then sometimes, depending on the casino, there is 1 or 2 green spaces, right? That just gives the casino their little bit of edge. So if you bet on black and someone else bets on red, but it comes up green for the casino, they get everybody's money, right? That's that little bit of edge the casino gets. But we'll just for the moment say that it's half black, half red on a roulette table. So what happens is they post the numbers and they show you whether it's a black number that came up or a red number that came up. And so what happens is people walk by. This was found mathematically, and then the casino said, hey, we can get people to bet more. And the way a casino works, I think people don't always understand how a casino works. The casino makes sure that the probabilities for all games in their casino have a slight edge for the casino. So the casino is not really trying to beat you. Like a lot of times you think that you're in this like contest with the casino and I'm trying to win money and they're trying to win money. No, what the casino is doing is using the law of large numbers that says every game is slightly in our favor. So we just need people playing. The more we get people playing, the more money comes into the casino. Right? It's not like I'll hear people talk about, oh, they're strategically trying to win against you. No, their strategy was in setting up the rules of the game. And then they used the law of large numbers and says, if we can just get people to bet enough hands, the probability will favor us and we'll win. This is why, people will go, oh, doesn't it make the casino mad when someone hits the jackpot? No, not at all, because that gets everyone excited and betting more, which means that people will end up in the long run putting all that money back. Right? And you'll see this. Sometimes you're playing, someone's in a casino, they're up $500 and they're super happy. You keep playing all weekend, the casino gets the money back. Right? But people will walk by the roulette table and they'll look at those outcomes, those list of outcomes, and goes, red's come up like 7 times in a row. Black is due to hit. Right? You'll hear people use that phrase. It's due to hit. And then they put money on it. But that's not how probability works, right? That's thinking of the law of averages, which is incorrect. The law of large numbers just says in the long run, after thousands and thousands of trials, the numbers are going to get better and better. It doesn't say the next trial is going to make an adjustment for it. That's what people are saying when they say red is due to hit. But think about that little marble that they spin around the wheel on a roulette table. That little marble doesn't have a memory. It's not like sitting there thinking like, I've come up black 7 times in a row. I better come up red this time or the universe is going to be out of balance. There's no memory. There's nothing keeping track of what that ball is doing. If the roulette table came up black 7 times in a row, the probability of it coming up red on the next turn is still 1/2. And the probability of it coming up black is still 1/2. That probability doesn't change because of past events, because the marble it can't remember. It just has the rules of physics, the laws of physics are making that little marble spin. There's no part that comes into the equation. If you ask a physicist to figure out, okay, if we shoot the ball like this, where's it going to land? They're not going to calculate it and then go, oh, by the way, is the ball wanting to land on a red spot? Like, none of that makes any sense. So just understand the difference between the law of large numbers and the law of averages, because it's subtle, but it can mess people up a little bit. Okay. And we'll state this formally here. The law of large numbers applies to behavior over a large number of trials, and it does not apply to one outcome. Right? The casino knows that that's how people's brains want to think, especially people who don't understand statistics. And so they use it to get you to stop and bet on the roulette table. That's exactly what the sign is there to do. Don't make the foolish mistake of losing large sums of money by incorrectly thinking that a string of losses increases the chance of a win on the next bet. No, because if you're playing most casino games, that's not how it works. 42. Okay, let me just see where we want to get to. I'm trying to think of anything important I can throw in there before I next see you. I think with what I told you, I think you can get through most of this stuff. Complementary events. A complementary event is just the opposite. So let's say we're rolling a dice, and the event that I'm looking at is rolling an even number. Then what would the complement be? It would be rolling an odd, right? Complements can be really helpful because you can calculate them indirectly. Because the whole sample space has a probability of 1. All the outcomes together, if you add up those probabilities, it equals 1. Well, if I know that my probability is 1/2 and the whole sample space adds up to 1, then I can calculate the complement by taking 1 minus the probability of getting an even to get the probability of getting an odd. Right? So if you've already calculated that value, you can get the complement by just taking 1 minus that. And sometimes that you can make problems way, way easier that way. Right? So you'll see some problems like that. So the complement, more important than people tend to think. I just want to make sure that we got to move. Oh yeah, there's odds. We're not going to worry about odds too much. We want to be generally thinking about the things in terms of probability. So try to always put it in terms of probability. In fact, the reason that odds come up so much is that as confusing as probability is, most people find odds even more confusing, which benefits the casinos, right? If you're going to go bet on sports, like if there's sports book, you're going to bet on a baseball game or a football game or something like that. A lot of times those are given in terms of odds. And part of that is because I think people get confused with odds a little bit. It's less mathematical thinking than, say, probability. Okay, with 5 minutes left, I don't think, let's see if there's anything I can talk about in 5 minutes. Yeah, we can't get into this. So there are ands and our ors. We'll leave off with that. We'll talk about that next time. Pretty important because there are ways where you can start calculating way more complicated probabilities, but there's some rules that go along with it. Okay, so thanks everybody. Make sure you're getting caught up on the homework. Be aware, the chapters are going to start coming quick, so I highly recommend you don't wait until the last minute because it's probably in your benefit. If you can get through one chapter, get through it and start the next one because they're going to start coming pretty quickly between now and the end of the semester because they're short. So it might seem like, why are we blasting through chapters now? Well, if you look, some of the chapters might only have like 3 sections, and then one of them is, we just cover enough to understand a couple basic principles. So it's going to seem like stuff's coming quick because it is, because each chapter has a little bit less to it, which means we're covering more chapters overall. Okay, so we will leave off right there. Anyone who wants to hop into Zoom and talk to me about anything is welcome to do so. Otherwise, I will see you in a couple days. Thanks, everybody.